Good afternoon, everyone, and welcome to this week's Monsoon Cafe. So today I'll be talking about monsoon depressions with special focus on some general propagation theories that have been given over time. And in the later part, we're going to talk about the anomalous tracks and what are those anomalous tracks and how are they different from a typical propagation that we mostly see for a monsoon depression. So So before going to the talk, so firstly I want to to show how a monsoon depression typically looks like as seen from a satellite. So this is one video image of a monsoon depression that happened on 17th July this year, 2025. You can see this cyclonic vorticity, the cyclonic structure, along with these cloud bands. You can see how they're moving in the anti-clockwise direction. And a snapshot of this particular depression is seen in this particular image, which is taken on 18 July, next day. So you can clearly see this cloud bands across this depression, and which is a typical structure of how a depression would look like if you look it from a top view. Now, in order to understand this, how a depression is actually internally, this is a schematic taken from a paper by Hunt et al. In 2016. They're given a very good schematic regarding how a depression structure looks like. So there is a cyclonic rotation, the cyclonic vorticity here, the lower levels, and it extends up to around 200 hectopascal, depending on the intensity of the depression. Above that, there's an anticyclonic circulation and a divergent outflow. There's a large cloud cover at a at higher levels. The distinctive feature is this particular warm core over a cold core structure of temperature is seen. It's a very unique structure with a depression. Apart from that, there is a high PV anomaly core that sits around the center is around 500 hectopascal and the secondary core around 700 hectopascal. So this is a typical structure of how a monsoon depression is. And since we're focusing more on the propagation theories, so this is the track of all the monsoon depressions that have occurred from 1980 to 2020. And this is taken from the IMD EATLAS website. And you can see majority of the tracks are towards this northwestward direction. So almost 80% of the systems form in the Bay of Bengal region, and the rest 20% is from the Arabian Sea and overland. So you can see majority they move in a northwestward direction. So people over time have tried to understand this particular propagation and they came up with some theories. So I will be talking about two theories regarding monsoon depression that has been postulated in this particular century. So the first is a theory by Chan and his team way in 2005. Where they have talked about westward propagation of the Indian monsoon depression. Note that they have typically used the word westward instead of northwestward, which is the more similar propagation that we mostly see. And the main line, like the main hypothesis of their talk is being highlighted here. So they said the depression is propagated westward by dynamic interaction between the convection center and the monsoon disturbance. That is basically the depression itself through the negative stream function tendency. So negative stream function tendency has been considered as a proxy for propagation of a depression. And they tried to address this, means they tried to show this hypothesis with the help of a schematic here. So in the schematic, the left-hand side is basically the monsoonal winds, the zonal structure of the winds. And the right-hand side, you can see the cylinder is the core of the monsoon depression. I consider it largely as a monsoon depression, which has been, you can see it is marked as a negative stream function. So negative stream function means that there's a positive relative vorticity here. And the idea was that this secondary circulation, which is marked by the rectangle here, this secondary circulation is what is trying to maintain the water vapor that is coming in this particular region. So they said that there exists some sort of a secondary circulation around the depression, which is an east-west circulation. And this circulation maintains the water vapor moisture anomalies that comes in this particular region towards the downstream of the depression. And since there is a convergence in the lower levels. The moisture converges here, it goes up, and it fuels this convective activity towards the west of the depression. Now, the convective activity shown here is to the west. It's mostly because there have been studies that have mentioned the presence of convective activity higher towards the western side of depression. And so in time, because of this convective activity, there results in generation of latent heat. So latent heat again kind of acts as a feedback to the organism itself, and it tries to maintain this asymmetric circulation, this secondary circulation around the depression. So the resultant, this convective activity results in a low-level vortex stretching, and in time it creates resulted in a negative stream function tendency to the west of the depression, hence resulting in the shifting of the depression itself. So this is a very simple theory that I've tried to explain using different budget equations, and they've come up with this in 2005. So after a decade later, Booz with his team came up with an alternate theory of monsoon depression propagation. They said that it's an adiabatic westward drift of a monsoon depression. So the main line of this means the main thing of this theory is that they have considered a monsoon depression as a potential vorticity core, and this potential vorticity core propagates westward by nonlinear horizontal adiabatic advection, basically a beta drift. Now, the beta drift is a popular theory in the context of cyclones, tropical cyclones. So I will not go into the details about beta drift, but it's basically the interactions between the planetary vorticity and the vorticity of the synoptic system itself. So for this, they initially tried to disprove the original, like the earlier theories of depression moment, and they plotted the lower level vorticity equation, the different terms of the vorticity equation. So this is the tendency term of the vorticity equation, 850 hectopascal. And they found that the vortex stretching term, which was earlier postulated as the leading term or the dominant term for the propagation of a depression, this term doesn't actually act to get the required directional perspective, but it is just trying to act opposite to this vertical, the horizontal advection term. And so we cannot directly postulate the stretching term to be the dominant factor in case of a depression moment. So based on this, they tried to disprove the earlier theory, and they came up with their own theory of the beta drift thing. So they calculated winds very close to the potential vorticity core. So their idea was that whatever the potential vorticity core, the maxima is at a particular level, that maxima is being advected by some winds, and those winds are basically resultant of the beta drift effect that we mostly see for tropical cyclones. So they calculated the winds U and V, and they did a zonal distribution plot between the storm velocity. So this storm velocity is calculated from the track dataset that they have utilized, and they found that the majority of the points, it's a mode of this particular distribution, lies in this 1:1 line. That basically suggests that the whatever storm velocity we get at 500 hectopascal, or whatever storm velocity we get, they are almost similar to the PV weighted winds that they have calculated based on these particular equations. And thus their hypothesis remain robust over time. So this is a 500 hectopascal, the zonal and meridional winds. And this is 700 hectopascal. They have looked into the secondary core too, in order to check if this hypothesis remains constant. Although there is some shift in the number of data points, but you can see overall it comes out to be fair and large good in case of understand the general propagation of a monsoon depression. So till now, mostly people have talked about monsoon depression propagation in a mean sense, highlighting the fact that it is mostly driven by the winds that is close to the center and at the mid level. But do we always, that a simple question comes to my mind, like, do we always get a monsoon depression that is moving in a northwest direction only? So for that, let's just directly look again to the track image. So this is the same image that I showed earlier in my slide. And if you look closely, you can see that there are certain tracks that are kind of not moving in the northwestward direction, especially the depressions that are in the Bay of Bengal, and they sort of move in the northeastward direction or in the northward direction. So, and the presence of these particular tracks have been noted in multiple studies dating far as back as 1977 by Dr. Sikka, where he said that the strata of these tracks in the months of June and September are larger, and these 2 months results in a recurvature of depression tracks. So based on this particular observation, we sort of wanted to look in those specific northeastward moving cases and wanted to understand how these cases are different from a typical northwestward moving depressions. So for this analysis, firstly, we identified northeast moving cases. We considered a dataset from 1982 to 2019. And out of them, we identified only 6 northeast moving, prominently northeast moving cases. Now the number of systems are fairly low as compared to our typical northwest moving patterns, but still we wanted to look more into the anomalous cases in order to understand the depressions better. So for our study, we have considered these 6 cases of northeast moving depressions as shown by this magenta color track. And similarly, for a comparative study, we have also randomly considered 6 northwest moving systems, which is shown by this black track. And note that all these systems are in June and September. So our time domain is mostly in the months of June and September. And all these systems are originated beyond 80 East. So if you look at the internal structure of the depressions, so this first figure is basically the mean composite plot of relative vorticity anomaly for all the depressions that have occurred in June and September. The second plot is the same relative vorticity anomaly curve for the northeast moving cases, and this is for the northwest moving cases, the combination that I've considered. So one difference in all these plots is that these northeast moving cases are typically has a more deeper relative vorticity core as compared to the northwest moving case and also to the mean case, which suggests that these systems are fairly stronger systems as compared to the mean case also. So this is the first observation that we found. And secondly, if we look into the moistatic energy anomalies at 50 hectopascal, we also find significant variability in the spatial distribution of the MSC. This is the mean plot for the MDs that have occurred in June and September. And you can see that the spatial orientation is almost similar to the northwest moving cases, which is more oriented to the northwestward direction. But in the northeast moving cases, you can see that the anomalies are more oriented to the southeast or south quadrants, which typically gives us an idea of the difference in the spatial distribution of MSC, or you can say in the lower level is mostly driven by the moisture. So this is one striking difference that we got, and this made us analyze more into some thermodynamic parameters to look how they are thermodynamically different in the context of northeast and northwest moving cases. Yeah. So we look into vertically integrated heat source and moisture sink terms. So heat source and moisture sinks are basically the residual term of the thermodynamic and moisture equations. And what we did is that we divided our depression into 4 different quadrants, C being the center of the depression. And we will focus on the first and the fourth quadrants for now. We see that the northeast moving cases have higher values of Q1 and Q2 as compared to the other quadrants. And you can see that for all the variations of Q1 and Q2, the highest variability, the primary contributor is coming from this vertical advection term of temperature and moisture. So it suggests that there is a strong vertical coupling at different levels, for especially for northeast moving cases in the first and the fourth quadrants. The highest variability mostly comes in the third quadrant, Q1 and Q2. You can see from this particular plot. And this makes sense because the maximum convective activity is more concentrated to the southwest quadrant. Hence, this variability is more in this particular quadrant. So again, this sort of gives us a perspective that in the northeast moving cases, this depressions doesn't have rainfall convective activity more localized to the west of the depression, but there is also strong convective activity to the east of the depression itself. So this strong convective activity could again may result in some vortex formations or low level convergence that could potentially lead us to a conducive environment for the depression to move. So this is one very distinctive difference in the northeast and northwest cases. So these are internal variabilities of both these combinations. And if you go for the large scale atmospheric features, how the large scale features different for different depressions. So this is for the northeast moving case and this is for northwest moving case. What we have plotted here is a zonal vertical wind shear. So in the northwest moving case, you can see the positive wind shear kind of comes down to around 22 degree or 23 degree north in the west and central India region. Whereas in the northwest moving cases, it is mostly located beyond 25 degree north. So there is a difference in the upper level structures also, because like this is a zonal wind shear. So it's basically the winds at 200 hectopascal minus winds at 850 hectopascal. So we cross-checked this and we found that the winds at 200 hectopascal sort of gave us this perspective or this variability in the spatial structure. So this made us to look into geopotential and wind anomalies at the upper levels. So we have considered this as 300 hectopascal. And a very dipole kind of structure is seen in the case of northeast and northwest moving cases. In the northeast case, you can see there is a strong negative geopotential anomaly that is centered around 37° north, and it comes down up to 25 or in the 22° north too. This anomaly, negative anomaly you see, is basically the composite mean of the depression itself. In the second case, in the northwest moving case, I can see there is a positive anomaly that sits here. The center is around the same latitude, although it is slightly shifted to the east as compared to the northeast move anomaly. And this difference in the upper level structure of geopotential and wind anomalies gave us an idea that the inhibition of this particular depressions when it is occurring towards this particular direction and the modulation of this depression through these winds could maybe add a directional perspective to the depression's movement, and thus the depression could move in this particular direction rather than moving in its typical northwest direction. So in order to know more about these geopotential anomalies, we did like composites of this similar geopotential wind anomalies at 300 hectopascal from day -4 to day 6. Now here day 0 represents the day of identification of the depression itself. And this day 0 is considered based on the track dataset that we have used. And we saw that this geopotential anomaly, which is more prominent at day 2, 4, and 6, this anomaly is a part of this extratropical geopotential anomaly wave train that you see here. So basically, geopotential anomaly wave train that is extends to the subtropics, and it sits there over day 4 and day 6 until it maybe decays over time. And similarly, for northwest moving cases, we can see the similar type of anomaly, but it's opposite of what we see in the northeast moving cases. We see that there is a positive geopotential anomaly, which is there at day 2, 4, and 6. And again, this anomaly is part of a large scale, extratropical geopotential anomaly, which is mostly seen in the upper troposphere. So this made us understand more that in despite of the internal variabilities being different, there's also that effect of a large scale variability that comes into play during the propagation of these depressions, and this mostly results in that difference in the directions of the depressions for the northeast and northeast moving cases. The structure itself is different in the large scale, so they will mostly modulate by some interactions of the winds of the depression itself and the large scale, which would lead to depressions to move in this particular northwest and northeast directions. So that's it. Thank you.
For after this, westerly wind at current Libra, only possible because most of the winds are easterly at higher level.
No, it was easterly at 200 millibar. Westerly 200 millibar.
No.
This one was.
You said
Yeah.
winds at 20 north are dominant wind and are westerly up to 20 north. But
Yeah.
at 220 millibar, there is a lot of easterly jet.
Yeah.
So you're not considering that.
No.
It is embedded in a jet, right? There's a jet there.
Yeah. Yes.
So at the higher level, that jet is strong or not?
Yeah, I think it's beyond 200 the jet depression, because one thing is that we notice these depressions that have occurred. So it's basically a phase during the early June and the late September. So it's like the onset hasn't happened so far into the central India region. It's either the onset hasn't happened, the onset has stopped over this particular region. So we thought that the winds, because of this intrusion of these winds, westerlies towards this particular, coming down towards this west and central India region, that would mostly modulate the depressions or like inhibit its movement towards this direction.
Look at the coastline, also same thing, is it?
To coastal in this area?
Yeah.
In this area, actually, the winds are easterlies. It's mostly easterly. Because you can see from this diagram, it is mostly easterlies. Okay. So the depression, the typical track, what happens is it kind of moves, it starts from over here, it moves like this, and then it recurves. So after moving a little bit, let's say about the Bay of Bengal also, it kind of recurves, and this recurve we suspected is coming from the upper level winds. The importance of the upper level winds towards this propagation. Yeah.
So that is the shear that includes the lower level winds also.
Yeah, it includes.
So today's talk will be a little different. I'm going to spend most of the time paying tribute to Professor Sulochana Gadgil, who died last Friday. And many of you here are very young. You were not here when she worked here and made a major contribution. As all of you know, the Center for Atmospheric Sciences was established by Professor Rodama Narasimha in 1982. Okay, and then he went over to National Aerospace Laboratory as the director. So Sulochana took over from him in 1989. Now, in the beginning, we were all sharing our space with ecological sciences in a building next to the SERC. All of you know that. Then in the mid 90s, we were given this space, and the Sulochana had to essentially go through the getting funds and building this building. Okay, and so she managed some funds from DOD, Department of Ocean Development, which was at that time. And during that time, the number of faculty rose rapidly. Before that, the faculty in COS are all like me from some other department. I was in mechanical, and Professor Narasimha and Professor Prabhu were in aerospace. We had Iyengar from civil, so and from math and so on. So we had a wide spectrum of people. And once the center established itself, it had to have its own faculty. So she was involved in the recruitment of all the new faculty in the COS. And during that period, we started getting more students. And so she played a very important role in that period. And then she made sure that there was a review of the center after 10, 12 years. And this review committee recommended that the name has to change because you cannot do atmosphere without ocean, as all of you know that. So we became Center for Atmospheric Oceanic Sciences in 1996. Okay. And so I'm going to talk about some of the work she has done in the area of monsoons and agriculture. Okay. Now, I should tell you that she did a basic doctorate in applied maths in Harvard University. And her work was mostly related to flow around orography in the oceans, not atmosphere. Okay. Then she had the good fortune to do her postdoctoral with Jules Charney, the biggest name in our field. And here is a photograph taken in 1977 with Ed Sarachik, another famous name, Charney, Iguna Kalne, all of you know her. She's the one who had reanalysis, and Sulochana in some meeting in 77. She came back from Harvard in 71, and those days, there were no jobs available in India. Okay, you're talking about 50 years back. So the government of India had a, what do they call, CSIR pool officer. You come here, and as you're looking for a job, you can be associated with, like the Inspire Fellowship now in some sense. So she joined IITM as a CSIR pool officer. And before I go further on that, I must mention something about Charney. Charney is undoubtedly the superstar in our field because he was very good in analytical development of ITCZ, for example, and also was the first person to be involved in weather forecasting in Princeton. And they started forecasting in late 1940s. He was very much in it. Okay, so he is the one of the biggest names. So she was inspired while working with him. And so our interest shifted over from ocean to ITCZ. Okay, so throughout her life, she focused on ITCZ because of Charney's inspiration. Now, all of you must look at this paper. It's a very old paper going back 54 years. Okay, and remember, this was an era computer was hardly there. So Charney developed a very simple model for ITCZ with a boundary layer a few kilometers at the surface, another boundary layer near tropopause. Okay, these two. In between, there's nothing. And it is a very elegant piece of work, analytical, using what at that time was called singular perturbation techniques, which are techniques used before the computers became common. So if you look at the paper, it shows how there's a strong meridional wind near the boundary layer, and then there is strong wind at the tropopause. In between is nothing. Okay, a lot of people are surprised by the result. It's a unique result, like this and then like that. Okay, but today you go look at reanalysis is exactly what he developed. So it's an amazing achievement of Charney. And another person who influenced Sulochana a lot was Devraj Sekar, who had spent all his life in India Department. He had a lot of experience about depressions and lows, about which just now Samudra made a presentation. So he was man experienced in monsoon synoptic systems. And Sulochana was the person who had got interested in ITCZ. And both of them decided to start looking at satellite data. Satellite data had just begun coming. But I must tell you, because all of you are in a different era, at that time, there were no big computers. There was no software available to process as all of you do now. She had to look at individual photographs of satellite visible data day after day and by hand plot the ITCZ. Okay, you get a cloud picture and you decide where the highest cloud is, and this is a tedious work, but it was done meticulously for a period of many years, and so this is the kind of cloud picture you get in the visible. Okay, and this was the period she used was 72 to 76, just 4 years of data, not much. And today we can generate the figure in 1 minute. All of you can do that on your computer, right? So based on that, they wrote the first important paper on how clouds move in the Indian region. And this is a famous paper, all of you know about it. It's a highly cited paper. And but you must remember the amount of effort went in because of the kind of infrastructure that existed those days. Okay. And this is what we generate today. In 1 minute, we can look up IMS data and show the picture. Now, this is what she showed for the first time, that in the Indian region, there are two cloud bands, which one near the equator and one where it comes from our region. Okay, and so she was able to show that over the period, the ITCZ which resided near the equator traveled all the way to India and then went back on a long time scale, not synoptic. And then she looked at individual years, and you can see here these 5 years of data. She plotted the variation and showed how many times this ITCZ moves north. Okay? And so this was a major breakthrough in thinking. Before this happened, most meteorologists in India did not know that the clouds came from near the equator because they had no data. If you have no satellite, your view of the world is very different. Okay? As a matter of fact, because all the data was only over India, a lot of meteorologists thought that the center of gravity of the monsoon was India, which is not true. All of you know today, the main rainfall is occurring on Bay of Bengal. Okay? So you must remember that without satellite, our view of the monsoon was very limited. Okay. Now this is what you get today, again in 2 minutes of using IMS data. It looks very nice and elegant, but what they did was much more difficult work because neither the data was available in digital form nor the computer was available. Okay. So I want to remember that. Same thing I want to remind you, which I told earlier, about MJO. I'm always amazed what Madden and Julian did. They had just a few data of surface pressure along the equator, maybe five or six stations. Based on that, they figured out the system is moving around the globe. Now, that's a marvelous imagination. Same thing about Walker, another amazing guy, Gilbert Walker, which are the few stations in the world he thought he was able to figure out there's a southern oscillation, northern oscillations. So all the major modes we talk about today, he discovered 100 years back. Okay, so these are people with great imagination but limited data. Okay, now the next important work Sulochana did was again a very important work, the role of sea surface temperature. Okay, again she had very limited data over Indian Ocean, SST data. Based on that, she argued that before 28 degrees centigrade, as SST goes up, cloudiness goes up, but beyond it, it is independent of SST. Okay, that's a very important result about the threshold beyond which deep conversion occurs, and the fact that once deep conversion occurs, SST becomes irrelevant. Okay, so again, this is a remarkable piece of work with only limited data in only one ocean. It was later extended to all over the globe, and again today, people have done a lot of work based on all our data, this data over many years, and they have documented the same phenomena for India, Pacific Ocean, all of them show very similar trend. Okay. So this was again a very important piece of work, and so it's highly cited. Now today, of course, you can plot this result very easily and show how the West Pacific and Indian Ocean are all about 20 degrees centigrade. So they don't depend on SST. You see a vertical line. But you look at East Pacific, very cold, all of you know that. This is the Indian region. And so here, the rainfall in this case increases sort of linearly up to 2028, and then it starts picking up. And Atlantic is sort of in between. So this is a nice result today. We can get it. And if instead of SST use water vapor, which is my favorite, you can see it collapses, sort of, not completely, but almost. So today you will relate rainfall to water vapor, not SST. But at that time, there was only data available. Then she wrote an important review paper, which is the most highly cited paper I'm aware of in this field, which is a review about Indian monsoon, where she strongly advocated the view of monsoon as not as a land sea breeze, as was proposed by Hadley and so on, but as a movement to RTCZ. Okay? So this is highly cited because of her totally different viewpoint she made. This is about 22 years back. Then her major achievement, of course, after that, we had some collaboration with Peter Webster, who was in Penn State, and she wanted to understand the mechanism of northern migration. For that, you need a model. And so we adopted the axiometric model of Peter Webster, on which I worked. And later, Ravi Nanjande continued that work using a parallel computer developed at NAL. Now, you must remember that in those days, the computer power we had was much smaller than what's available on a laptop, right?
Mobile.
Yeah, on a mobile, yeah. So we had to struggle, so we had to use parallel computing, we had developed new techniques. And so we came to know about the mechanism of northern migration of these ITCs. Then in 1996, she started something very different. And I must give you my personal, because I was sitting in the door opposite to her. She was along this corridor on the other side. She got, I will not name the person. I don't want to get any names here. She got a letter from a foreign scientist telling her that he will be happy to help India develop its climate research program. Okay. Now, Sulochana as a patriot, she asked herself, after 50 years of independence, why should Indians depend on somebody else to tell him how to write a climate program? She decided to stop all research and devote the next 6 months to write a program of how India should develop its climate research. Okay, it's remarkable achievement of one person essentially. But she was very pragmatic. She realized that for this program to be realized, one person vision is not enough. You need people to cooperate. So she interacted with Dr. Pant in IITM and of course Devraj Sikka. And finally, the full document was written and she identified 3 areas. One, of course, is monsoon variability, which is very important, both synoptic, intra-seasonal, seasonal, and so on, intra-annual. So that was one focus called more. Second was past climate change, because some work was already going on in India on paleoclimate. So she got that. And also, of course, climate change. This is in 96, already climate change became an issue. And then she added something of her own interest, climate and agriculture. So these are the three main themes of her, and in all of them she did contribute. Okay, and because of that document, ultimately DHA decided to support. Before that, I must tell you, 40 years back, there was hardly any funding for research on monsoon. Okay, and you must remember the state of condition in India. The India Met Department was under the Civil Aviation Department. Okay, remember that. Dr. Joseph, a colleague of Salochana, who is about 90 now, he used to mention that for every minor thing, they had to go to civil aviation for getting anything. It was a very tough situation. So research was confined mainly to IITM in a very limited way. Funding was almost non-existent. Okay, I remember I was in the governing council of IITM at that time. They had difficulty giving salaries. It was that tough. Okay, so this program was a big boost. Once this document came out and DHA was convinced that there's a need to fund research on climate, money started coming in. And for the first time, India planned observational program. Before that, India was involved in collaboration with other countries. Our famous monarchs of the most well-known program was the international program. Okay, because we didn't have ships, we didn't have anything. So our scientists participated, but the real leadership and real thing came from somewhere else. So this was the first time, because of that document, that India planned an experiment both in the Bay of Bengal called Bobmax and in the Arabian Sea called Ormex. And of course, the leader for all this was Professor G.S. Butt. Most of you know about him. And so the first time data was collected, and we were able to show the outside world that the data we collect is reliable. You must realize that since we were colonized for, I would say, 1,000 years, people don't trust what you do here. So you have to establish your credibility in the scientific world. So this was very important development, both Bobmax and Ormex. There were two more land-based experiments called Land Surface Process Experiment and then CTCZ in 2009. So over a 13-year period, a lot of data was collected and around the oceans around India. And so the infrastructure for measurement in India went up dramatically. And then we had establishment of INCOIS in Hyderabad and NIOT in Chennai. All these contributed to India development as a major observational where done. Okay. If you want to know more about this, you can read this report in Guess by Sikka and Sanjeev Rao, who was in DSC, about the Bobmax experiment. Okay. So this to me was her major achievement. In addition to our work on ITCZ, because this made impact not just here but the whole country. Okay. Now she also worked on our monsoon research, and she worked with both Dr. P.V. Joseph and M. Rajiv, all of you know him, on breaks, monsoon breaks. There are 2 or 3 papers, and one of these papers I discussed a few weeks ago. So this is a very important piece of work, again highly cited, because it is very important to understand the active break cycle of the monsoon, and they documented all the data over the last 100 years. Then she started looking at how the GCMs perform with respect to the Indian monsoon. Okay, here's a comparison of 8 GCMs, 3 of them that were used at that time. And the main point she made in these papers is there are years like 1994 where all the GCMs are wrong compared to observation. So this is a very important statement because some GCM being wrong, all of us understand. Some mistake in cumulative scheme, some problem here. But all of them are wrong. There's something wrong in the formulation itself, right? Because you can't blame one scheme or the other. So this clearly showed the need for improvement. And so this was a very important development demonstrating that there are occasions when the model fails completely, all models. Okay. Now, he also did work for surrounding countries. She did visit Bhutan. And I was impressed by his result is, you all know the ISM model. Okay. This is very different. Look at the number of below. I'm really amazed. I wish somebody would work on it. It's a small region, not easy to do. But today you can do much better GCMs and so on. So this is very interesting. Why Bhutan seems to have more below normal monsoon years than good monsoon years. Okay. Of course, orography plays a role there. So you require a high resolution WRF to look at it. Somebody should look into this issue. Okay. Then other things she did, all of you know that CAOS was well known for the discovery of the Indian Ocean dipole. Three of the people from here were involved. Saji was a student here, Vinay, who is the chairman of CAOS now, and Goswami, who was a professor here. They wrote a famous paper in Nature identifying phenomena in the Indian Ocean comparable to that in the Pacific Ocean for the first time. Okay, and Sulochana saw that that discovery was mainly focused on the ocean. Okay, so all of you know that in the case of the Pacific, there are two phenomena which are coupled: the El Nino phenomena in the ocean and SO, Southern Ocean in the atmosphere. And as all of you know in history, SO was discovered a long time back. And El Nino was known to oceanographers some time back, but they didn't see it together. Only when the two were seen together in the 80s, it became ENSO. Okay. Similarly here, IOD had to be linked to a phenomena in the atmosphere, which we call equin, equatorial Indian Ocean oscillation. Is a name, like instead of SO, equinoria, but she found it easier to characterize it through the zonal wind in the equator. Okay? Now, the reason what was done was, in the case of the Pacific, Walker was lucky. There were two stations, Darwin and Tahiti, which were going the opposite direction, right? India does not have any station along the equator. So you have to have done winds. So that worked out okay. And then she showed that if you combine the equin, which is a measure of the IOD, and ENSO, which all of you know, then we can essentially, in the phase diagram, explain all the extreme events in the Indian region just using two parameters. This to me is a great development, showing that most extreme years one can connect things. But the interesting thing here is that she left out all the normal years. Okay, because normal years more complicated and more work needs to be done. If equin and ENSO go in the opposite direction, then the cascade is a drought. Okay, you got a normal monsoon. So I'm convinced that although 70% of monsoon are normal, they are not normal because everything is normal. They are normal because two external forces went against each other. Okay, so this needs to be addressed. Partly Arindam has done some work which gives that impression, but I think more work has to be done to look at the remaining 70 years, which are normal, in which these two were actually in the opposite direction. Okay? Of course, not all 70 years will be covered by that. Only some of them is worth examining that. Then the other part she developed because she had a wide interest, because her husband was an ecologist, she had a wide interest in agriculture. Okay, so although all of us know that monsoon has huge impact on agriculture, it was not really quantified. So our finance minister keeps saying Indian economy is a gamble on the monsoon. But how much is a gamble? Okay, so she quantified that, and to do that, remember that one of the great achievements of India is over the last 60 years, our production has gone up, food production, dramatically. Okay, and that's why we are able to assert our strength in the world of nations. Before, in the 60s, 70s, we were begging for food. Okay, because when I was a student in US, I remember how they looked down upon us because we were not able to feed ourselves. So this was a major achievement due to green revolution. But if you remove that effect, you will see this phenomenon, the role of monsoon. Okay, you can see that every drought, the production goes down by 10 to 20. I'll show that 10 to 20 million tons goes down, and it doesn't go down linearly. The most important discovery she made was the food grain production bubble anomaly is not a linear curve. Okay, it is non-linear. When it is below monsoon, your yield goes down dramatically. Okay, when it's above monsoon, it doesn't increase. That's partly, I think, our problem. The good monsoon years we're not fully able to utilize. In the bad monsoon years, because 50% of the food production is rain-fed, we suffer heavily. Okay? That is the reason why this curve goes this way. But still, one has to ask why we're not able to utilize the high monsoon years. Then the other thing she did was remarkable for a professor in IISc. We all live in our own world. We have our own interests. We don't interact too much with the outside world. Okay? She was different. She went to Anantapur district in east of Bangalore, and she was lucky that one of the students working with Mother Gadgil was a farmer. Okay, so he was talking about the problem farmers had in Anantapur district, which is, if you look up the rainfall pattern, is very poor rainfall region. Okay, and half the year is drought, and so they grow groundnut, which is supposedly easier to grow than wheat or rice. And she met and talked to the farmers and tried to find out how to help them. Okay, and I must tell you, she was the first person, as far as I know, who invited these farmers, most of them were poor, some of them were illiterate, to IISc for a workshop. And this was a unique achievement. One of the leaders in that, I think this guy, he got up and said, I can't believe that India's foremost scientific institutions has invited us to come here and talk to us. So to me, that's a breakthrough in thinking. So she invited them. There's a discussion. Of course, there was a language issue. They mostly spoke Telugu. So Sheshagiri, the farmer, knew both English and Telugu, so he translated. So the discussion was very, very interesting. And one of the farmers who was doing well, he made a very interesting comment, which even I remember after almost 30 years. He said, yes, most of the years are bad for us. But in 2 years of good rainfall, you have to make enough money to survive the remaining 8 years. He was doing well. He was the only farmer doing well because he was smart. He said, my other friends, when they make more than 2 years, they spend it in many other things and they're in trouble next year. I am careful with my money, so I know that the 2 years of good rainfall has to take me through. So I want you to see the interesting difference between Anantapur and rest of India. All India rainfall, if it's above normal, our production doesn't go up. But when you talk about groundnut in Anantapur, it is dominated by high production in 2 or 3 years. So it's a very interesting scenario, regional versus national. Okay? And then she looked at it in great detail about the groundnut, how it works. Now, like all of us have GCMs to work with, the agricultural scientists have gone very far. They have a model for each grain, depending on its genetic component, everything. They run the model with incoming solar radiation, and they didn't include, Silosa included pests and diseases also into the model. So you predict, for example, this model, you predict what is the highest production possible. Okay, according to theory, this is like Carnot engine in thermodynamics. That's the highest. You cannot exceed that. That depends on incoming radiation and the genetic of the crop. Everything else, rainfall is perfect, everything perfect. Then you look at the actual output from the farmer. Of course, it is below that because the actual situation is different. But I want you to notice that in low rainfall years, the farmer's yield is higher than theory. Okay, that's very interesting. That's because this is a simple theory. It does not take into account intra-seasonal variation. It just takes the total rainfall and does it. Now, if you want to really understand real world, you have to account for it. For example, in a year in which rainfall was normal, but the distribution was abnormal, you won't get good yield. Okay. Farmers are quite smart. They look at when is the onset and they look very carefully. Today they look at IMD forecast and make decisions accordingly. Okay. So it shows that in poor rainfall years, farmers are doing better than theory, but in most good rain years, they are doing very poorly compared to this. Now, this is not surprising. So this she looked at into great detail. This is a comparison between model output, ideal output, versus grain yield in a agriculture research station, which is government maintained. Okay. Now, in a research station, you're not a farmer. There is no restriction on money. So you put all the water you want, you put all the pesticide, all the fertilizer, everything is perfect. So they're able to match. Okay. So what it shows is, if you have money, if you have water, and if you have all the facility, of course you can do as good as theory. But in the real world, this is what's happening. This is the district output, not the research station. So the real reason why output in India is low is because farmers don't have enough money to put fertilizer and pesticide. Although it's bad to use it, still they can't afford it because they're expensive. Okay. So this, because of that, she tried to develop some of the heuristics to help the farmer to manage better. Now, for all the work she has done, of course, she has got many awards, including the award in project sciences in 2008, I think, from Sheila Dixit. She was at Delhi, and later on in 2016 for the Lifetime Achievement Award. But I must tell you that she's not a person who got awards or publications or impact factor or citation. All those things are a new phenomenon. 40 years ago, nobody worried about that. So she worked because she enjoyed working, and her major contribution to me is not just her own research contribution, her ability to work in a team, both here and as well nationally, to advance the research in monsoon in this country. Now, this is not everybody does not have the skill. There are a lot of very brilliant people here in this campus, but not everybody can do teamwork. Teamwork demands a certain personality skill. You must be able to deal with people at various levels of ability and able to appreciate everybody's input to contribute to the total. Okay. So in all these field experiments, you have to deal with a number of agencies, number of people, and you have to be very diplomatic and you have to be very careful. So this is the ability I know only two will have, Professor Narasimha and Sulosima. And that's why these two people have made so much contribution to India's growth in monsoon research. Okay. Now I want to end by a comment from Warren and Albert's book on thermodynamics. Sulosima fought oral life for promoting the idea of ITCZ and not Lancy contrast. But even today, you see any paper, they talk about Lancy contrast. So it's not easy to displace a very old theory. Okay, takes time. Okay, I think another 20, 30 years will go away. Right now, you see any paper, every time Lancy contrast, all that's completely irrelevant once the onset has occurred. There is no Lancy contrast, it's in the opposite direction. So, but old happens very hard. So this quote from Warren and Albert is relevant. If any of you have not read this book, it's one of the best books in thermodynamics you can ever read. Okay. Now let's come back to this week. We have come to the end of July. Half the monsoon is over, and the cumulative thing is 6.6 above normal. You look at July, it's now 5% above normal. They started very high, of 5%. Now I want to remind you that I made a prediction of 9% above normal, and it plus or minus 4%. So they are correct. Forecast was right. It's above normal and 5%. And other interesting thing here is notice that south is now normal after a few heavy rainfall events. All the other only east northeast is normal. But what I would like is I don't get it. I would like IMD to put out their forecast for every region. My curiosity is, yes, they are right overall. But are they right in each region, or It's just luck that things average out. It's very important to know that to not improve the model. Okay, the model got all the regional things correct and the total right. It means the model is very good. But a model got regional thing wrong, but somehow things added out, statistically added, then that's not good. So I hope one of these days they will put out their forecast for every region, the 4 regions that we're talking about. Now you can see that the monsoon core region is doing very well, except for the late onset in central India due to hiatus, and then a small weak-level monsoon in the middle of July. Then it records dramatically, and it will end on a very good note here. Now comes August. Now, all indication I showed you in the last few weeks that August is going to be below normal. Okay, and let's look at the forecast. One of them went out of scale. Okay, the 16.1 notice July. So I could show it on the scale. So it's completely wrong. I don't know why. So this week, I would say the model is done not so great. These it is okay. Way out here and way out here. And but I think this is going to now start declining as you go into August. And you will see why. Now, this is the forecast for the 1st to the 7th of August. You can see the central India will be well below normal. Okay. And weekly rainfall will be minus 35% all India. Okay, so that is going to be not very good. And this is shown more nicely in this district graph. There are no numbers to spoil it. This is how it was this week. This is 25th to 31st this week, and this is next week. See how it is changing. How this is going that way, and this is going this way. Very nice change in just 1 week. And this was predicted by most models about 2 weeks back. So that's a very good news. Now, what's the news about monthly mean? According to CAOS V2, the American version, it will be well below normal. Then this is pretty high, 10 millimeters per day, but the average is maybe 4 or 5 millimeters per day. This is CAOS V2, okay? And you look at September, it will recover slightly, as happened in the last few years. September will be above normal, but I don't think it will make up for August. But this light green is somewhere here. Okay. So let's look at a few more things. This is NCMR W which Ravi provided. And again, you can see clearly August will have a big below normal here. And September will be above normal. So this may compensate according to this model. Okay. And this is, we have seen it before, I'm repeating it. This is ESMWF showing that this from 29th, 28th here is going to be below normal right across all the way to Japan. Okay. So it's a very remarkable large scale feature. And this continues on the 4th to 11th August. Weekends 11th to 18th, and a new ITC that is coming from below. Okay. The low frequency oscillation. And again, this is large scale, not India. This is much larger. Okay. And it moves north, and I think by September, it's going to move. So that's why September is going to be good. The September, the system would have, another system would have moved across and come over to central India by end of August. Okay. Now I want to end this with a nice picture that I saw today. There are 2 cyclones because of China. Okay? And these cyclones came out of the ITC there. So that is that slightly curved, and from there this emerged in the last few days. Okay. So what is very interesting. Okay. So that completes my presentation, and I think next week is going to be Abhishek Brodala, right? Yeah. Okay. Thank you.